Okay, it says it's live.
Give it just a couple seconds. It's not quite 12 o'clock yet.
Oh, okay. I'll wait for your cue.
Okay, looks good.
Okay, here we go.
Exciting developments are happening in terrestrial microwave, aerospace, machine learning, contesting, education, and much more. There has never been a better time to be involved in amateur radio. You belong, no matter your level of technical expertise. Amateur radio brings together people from around the world. Being able to communicate on equipment that you may have built yourself with someone in a faraway country without relying on anything other than the ionosphere and some wire is a familiar story and a cherished tradition. Now, with 4th and 5th generation amateur operators in the United States, how are they getting on the air today? How did their radio experiments start? A common entry point is an inexpensive software-defined radio receiver called the RTL SDR. In the past, we might have built a crystal radio set and listened to stations after dark. Now, a ham interested in software-defined radio can download open-source computer programs that transform inexpensive thumb-drive-sized circuits into dozens of different radios that do everything from receive satellite signals to monitor local FM repeaters. In the past, you might have built your radio out of a parts kit. Now, you are just as likely to have programmed your first radio with an open-source DSP toolkit, such as GNU Radio. So once you have something like the RTL SDR, where do you go from there? Open-source software and software-defined radios are at the heart of what Open Research Institute, ORI, and Tucson Amateur Packet Radio, TAPR, do. Software-defined radios replace some or all of fixed hardware with software programming. This means that your radio can be a much more flexible device than traditional fixed-circuit rigs. This flexibility usually comes at a cost of additional power consumption and complexity. Once you are able to reconfigure a radio on the fly, the next step is to sense the environment and automatically adapt to the environment to achieve the best possible communications for the amateur operator. Both the Tangerine SDR from TAPR and the Phase 4 radios from ORI envision and incorporate some type of autonomous operation that makes the most of our spectrum. The Phase 4 microwave system automatically adapts the structure of the transmissions based on signal-to-noise ratio. When things are hard to hear, there is more error correction and simpler modulation schemes are used. When the signals are strong, less error correction and more complex modulation are used. This means maximum data through the radio at any time. The Tangerine SDR is fully capable of this type of operation, called adaptive coding and modulation, and more. The Tangerine SDR can be used to learn and predict ionospheric conditions, which directly contributes to our scientific understanding. ORI and TAPR are advancing the radio arts with fun and easy-to-use designs that put the operator first. In both cases, the radios can be accessed remotely. ORI's user interface is a web app, which means there are no software downloads, just to use the radio, and the visual style can be modified. If you need large fonts or high contrast, then it's there. Tangerine SDR can be used the same way. The Tangerine SDR allows you to monitor an enormous amount of bandwidth and easily find what you're looking for. The Tangerine SDR can receive and decode multiple simultaneous data streams, so it can listen on all bands at once for specific call signs. When one of these call signs is decoded, the software can send a notification email to you indicating where to find your buddy. How cool is that? One of the biggest challenges to enjoying software-defined radios is the learning curve. Advanced digital communications techniques can be complex. Cutting-edge techniques rely on advanced math. And this is where both TAPR and ORI can help. By making these powerful and modern radios fun and easy to use, some of the barriers to learning are removed. By using open-source designs, and by explaining the various parts of the computer code, even the most difficult math in the forward error correction and filtering can be seen, understood, and appreciated. ORI and TAPR are technical organizations that welcome volunteers at all levels. If you want to help advance open-source amateur radio designs and shape the features and functions of software-defined radios, please visit our websites to get started. ORI does research and development for open-source amateur radio, with an emphasis on the amateur radio satellite service. TAPR does innovative open source hardware designs with an emphasis on terrestrial and HF radios. Both organizations are registered nonprofits in the United States and work together. TAPR sells memberships, publishes a newsletter, and has an annual technical conference, and publishes a technical proceedings. ORI sponsors technical and regulatory work, including Phase 4 Ground, the M17 project, P4DX, Ambisat sensors, and more. You'll hear more about ORI in the second half of the forum today. And now, to talk about TAPR and Tangerine SDR, here's Scotty.
Thank you, Michelle. This is Scotty Cowling, and I'm going to give you the turbo whirlwind description of the Tangerine SDR project. It's a modular open source software-defined radio that I hope you find as exciting as I do. So what is the Tangerine SDR project? Well, it's modular open source, like I said, and it's a software platform. I envision lots of software mods to be going on over the years using the same hardware. It's all run by a group of volunteers led by TAPR and ORI, dedicated to the building of a pool of open source software-defined radio design info. Kind of like the OpenHP SDR project, if you are familiar with that. The following features are a hallmark of Tangerine SDR. The idea is to make it modular, so there's a wide range of cost-based performance options from about $300 to over $1,000, depending on what kind of features you want to add. All open source hardware and software, and it's really going to advance the state of the radio art, we think. So what are the components of the Tangerine SDR radio? Actually, it has 4 components: a data engine baseboard, kind of like a small motherboard. RF modules, there are 2 sockets for them, so you can use 2 of the same or 2 different ones. A socket for a clock module, and currently there's plans for one particular type of clock module, but we're open to future modules depending on the performance required. And a compute engine, which is typically a single board computer or a host computer, a remote computer. Not really part of the Tangerine, but as you're going to see, it's important to include this as integral to the Tangerine SDR radio as a system. So here's a block diagram. You can see where we have the 2 RF modules on the left, clock module on the right, with an FPGA in the middle doing the heavy lifting. And we've added a 3-port gigabit Ethernet switch so that you can hook it directly to the single board computer or the local host computer and to your local network all at the same time. So what features do we have? It's an FPGA-based gigabit Ethernet direct sampling receiver. We offer full receive coverage from 100 kilohertz to 60 megahertz. Being direct sampling, we convert the entire band at the same time. Very nice, easy to use web-based configuration program. So like Michelle said, no software to load. Your browser does the heavy lifting there. Multiple streams, as Michelle also said. We can cover all bands from 160 through 6 meters. And we additionally have a USB 3 port and a USB 2 port for expansion for things like RTL, DVB dongles, or additional high-speed data channel using USB 3. And currently, out of the gate, we're going to have receive capability, but transmit capability is a future option. We are planning for that. So you'll end up with a transceiver. This is the somewhat convoluted picture of what the thing will look like. The baseboard is in black in the middle here. The blue outlines on the top and bottom are the RF modules, which actually go in underneath. On the top, you have the clock module in the lower right and an I/O module in the upper left, which is compatible with a Raspberry Pi I/O module. And so you end up with basically a 3-board stack. That's the final Tangerine system. Then, of course, the Ethernet connector in the upper right, that goes off to the local computer, local host computer. And by the way, that's a 2-stack of Ethernet ports. So you get 2 ports. The third port that we were talking about, the 3-port adapter, the third port goes to the FPGA down here in the lower left. Okay, the RF module is kind of defines the RF performance of the radio. So this is the first RF module we have. And a little bit of an eye chart here, but that's the block diagram of the module that plugs in. Again, it's a pluggable module. Features of the module: dual 14-bit A to D at 122 megasamples per second. We have an attenuator on board as well as a low noise amplifier, and we have a fixed 55 megahertz low pass filter, which is removable in case you want to do undersampling. And we also have some onboard calibration noise sources, and as well as a user-defined plug-in filter. So if you want to lose the 55 megahertz bandpass filter or low-pass filter, plug in your own custom filter, or even if you wanted to plug in a preamplifier that is supported on the headers on the RF module. Future RF modules, personal space weather station receiver. We are thinking about doing that. Phase 4, well, actually, this is the first one. Personal space weather station receiver is the first one we're going to build, just a receiver. Then we're talking about many different RF modules to support the multitude of LSI receiver and transceiver modules that are coming out from Lime Semiconductor and from Analog Devices. So you'll see those coming along in the future. Next up, we have the clock module. The clock module was designed as a separate plug-in board so that we could offer a basic clocking system at an inexpensive price, or work your way up to a GPS disciplined oscillator at a more substantial price point. We're going to start out with a GPS disciplined oscillator because that's what's going to be required for the personal space weather station, but it's going to be a very high performance oscillator. And John Ackerman is going to talk on that right as soon as I get done here and give you all the lowdown on the GPS-DO clock module. Future data engine boards, we're talking about expandability since we're modular, so maybe larger and faster FPGAs, more RAM storage, maybe an SSD on board, and higher speed data ports. Its advantage of using gigabit Ethernet is it scales to 10 gig E, 40 gig E, etc. very easily. But same RF ports to allow you to reuse the RF boards, same ones that you have now. This is a real eye chart here, but it's put this in here for you to come back to for reference, and it's basically a comparison, price and feature comparison of many SDRs that are currently on the market today. I tried to limit the chart to boards that you can buy. They're typically boards, so I didn't really include full-blown radios. These are more like experimenter boards, and it's very difficult to compare a lot of these. You really have to go and look them up and look at the features yourself, because some of these, especially on the receive and transmit DACs, they have multiple channels. Some of them do, and so this chart is maybe a little bit simplistic, but gives you a good jumping off point to get a feel for some of the SDRs that are available today. Okay, so that said, what can I use it for? Well, the first application is going to be the HAMSI Personal Space Weather Station, but the plans are these other uses down here, like Michelle said, a Phase 4 satellite ground station. Perhaps we'll have boards for that. Definitely academic uses to teach SDR and FPGA techniques at universities. Amateur communications SDR, so you can basically pick the features that you want, plug them in, get the performance level that you want to pay for. Also, we will have a capability to do a remote ham radio, remote control, and it's really an up-and-coming feature of most SDRs these days. And there's a few interesting things you can do with this radio that I will get to toward the end of my talk here. So a couple examples. This would be the Personal Space Weather Station example with a mid-grade receiver. This is the module we're working on now. This is the GPS-DO we're working on now, and the data engine we're working in now. So this configuration will be first out of the gate. The satellite ground station, we would use undersampling on the receiver with an external LNB and an up-converting power amplifier at the dish. And basically, we could use the same receiver board, but we'll undersample, and we'll have a new transmitter board that will be a baseband transmitter board that then you can up-convert. Okay, or if you're an experimenter, you might want a more premium receiver or a more premium transmitter, and you may not need the GPS-DO function, but you might want a very low noise premium oscillator. So we will be able to offer that configuration. And if you just want to get your feet wet in SDR and you don't want to spend a lot of money, perhaps a basic low cost entry with low cost and lower performance receivers, but the same platform, the same firmware, but just a little bit lower performance for a little less money. So a little bit on the terrestrial weather station. This is just an example of a weather station, but we're thinking of the same kind of equipment only for space weather. So what would space weather have? Well, basically you want to listen to the ionosphere, and since we don't have a transmitter, we're going to listen to what they call signals of opportunity, which are existing transmitters like WWV, hams, broadcast stations, things like that, beacons. So with things like a lightning detector, total electron content receiver to measure the ionosphere. You've all heard of solar storms with traveling ionous disturbance. Well, you'd like to be able to detect those and kind of monitor what happens in the ionosphere to WWV, say, or other broadcast stations when there is one of these traveling ionospheric disturbances, and see if you can characterize them. And if we have a whole network of these all linked together via the internet, then we can get a much wider picture of what happens to the ionosphere worldwide during one of these disturbances. So if you're interested in that kind of thing, HamSci has a Zoom workshop coming up on March 19th, 20th. So go to hamsci.org and you can get lots more information on the science aspects of this. Of the Tangerine SDR uses. So what can I do with it besides a personal space weather station? Because that's all well and good, but what about my ham radio? Well, as Michelle touched on a little bit, we're going to have software and firmware to do a whisper monitor and an FT8 monitor, and these are really interesting because, like Michelle said, we can do simultaneous reception of all bands, and by the way, you can do that while you're using the radio as a personal space weather station. So you can monitor multiple slices of frequencies. So you could be on listening to FT8 and Whisper at the same time while you're monitoring a ionospheric disturbance, say up at 24 megahertz or some frequency, a higher frequency. And the interesting thing is, on the FT8 monitor, we have a feature where you can put in a call sign, and if the radio hears that call sign on FT8 on any band, it will send you an email telling you where that signal was heard and what band and what time, so you can connect with your buddy who just happened to appear on FT8 because, say, propagation opened up to the Midwest and you're out west, and now all of a sudden you can hear him. So interesting concept of working DX. And we'll be able to support full digital mode transmit operations once we build ourselves a transmitter. And another interesting thing is you can hook it up to your local home network, and you can have multiple radio clients hooked to the same radio using these multiple streams. So you could have a radio in your bedroom, a radio in your ham shack, and for you hardcore enthusiasts, the radio in your bathroom too. So what is TAPR's mission in all this? Michelle touched very good on a lot of that, but just to reiterate, we support R&D development with R&D funding and early volume production, and the result is we end up with a growing pool of contributors and experimenters, and that's kind of what we're aiming for. Our webpage, tangerinesdr.com. Please take a look and see if you can get excited about this as I am. Anyway, thank you very much, and we'll segue here to John, who is going to give you lots of details on the Tangerine SDR clock module.
Hi, this is an update on the status of the Tangerine SDR GPS disciplined oscillator clock module. The clock module for the Tangerine SDR has to provide accurate and stable sources of several signals, as shown here. A GPS disciplined oscillator is the best way to accomplish both the accuracy and the stability that we need. We generate a number of frequencies, both at RF, for the receiver and transmitter, and a pulse per second to use for time stamping. And we also wanted to make sure that this system could be used separately from the Tangerine SDR, because we think that the time nuts may be interested in a number of its capabilities. So just as a quick refresher, a GPS disciplined oscillator takes advantage of the fact that the GPS pulse per second signal you can get from many receivers is noisy. It has a lot of jitter in the short term, but in the long run, it tracks the atomic clocks at the U.S. Naval Observatory and the National Institute of Standards and Technology. Whereas a crystal oscillator is very stable in the short term. It doesn't have much jitter, but over time, it drifts and jumps around. A GPS disciplined oscillator tries to get the best of both worlds by using a phase lock loop to steer the crystal oscillator with the GPS. This chart on the right shows how this works. This is an Allen deviation plot. You can think of Allen deviation as sort of like standard deviation, although technically it's not. The x-axis is time logarithmically from 1 second to 100,000 seconds. The y-axis is fractional frequency difference. It's a version of parts per million or percentage. The lower on the y-axis you are, the better for performance. For its higher stability, low on the chart. As we look at this, the blue line is the pulse per second output from a traditional good quality GPS. The violet line is a temperature compensated crystal oscillator, and the green line is an inexpensive eBay oven oscillator. You can see that the GPS signal just keeps getting better over time. That's because the noise is averaged out and we get closer to the atomic clock performance. Whereas the crystal oscillators both are sort of flat at short term, but then they start to trend upwards as drift and other factors enter in. The idea behind the GPSDO was to have a bandwidth of the phase lock loop to catch these crossing points. And have the control essentially transition from crystal to GPS at the crossover. You can see with a low quality oscillator, the crossover happens at a shorter time interval. This is about 15 seconds. With a higher quality oscillator, the crossover happens later, and you need a much narrower loop bandwidth to take advantage of that. This is a diagram of the Mark I clock module that I was working on last year. I won't spend any more time on this other than to say that it's complicated and it had an FPGA, which means lots of ugly programming. After working on that, I was working on some tests on some modern Ublox GPS receivers, and we learned about maybe a simpler way to do things. The Ublox receivers have a time pulse output that's normally set to PPS, 1 pulse per second, but it can actually be programmed to more than 10 megahertz on these modules. The output of the time pulse at RF frequencies like 10 megahertz is remarkably good. It's actually much better than the pulse per second output, but there's a lot of jitter on the 10 megahertz signal. Its phase noise sucks, and you'd never be able to put that signal on the air because it would just be too ugly. But separately, I learned that there is a series of chips manufactured, I think mainly for the telecom industry, that are called jitter attenuators. And they're designed to be used as part of the clock distribution system in large digital systems. Basically, you have one master clock that's driving a whole bunch of boards, and each board needs to generate its own clock frequencies and needs to clean up all the noise that's on the master clock signal after it's bouncing around the room. And these jitter attenuator chips do that. They have an external oscillator of their own that's used to provide the short-term stability and the phase noise of the output while being locked to the reference signal that's coming in from the external clock. So you actually have a phase lock loop, and it works a little bit like a GPSDO might. The chips provide multiple outputs at anything from 100 kilohertz to over 1 gigahertz, and there are several outputs available depending on which chip you're using. So based on those ideas, we started from scratch with the Mark II clock module. We're going to use a Ublox GPS time pulse at 10 megahertz that's fed as the input signal to a Silicon Labs 5345 jitter attenuator chip. The PLL in that chip is actually acting like a GPSDO. The output of the chip is synthesized to the frequency we want, and that's locked to the 10 megahertz input, but its phase noise is significantly cleaned up. And the 5345 chip is great. It's got 10 independent outputs, and it can directly provide all the Tangerine SDR clocks, plus a whole bunch left over to use for other things if we want. This is a block diagram of the Mark II system, and you can see it's way simpler. Just a GPS feeding the 5345 chip, the outputs of the 5345 going to an interface connector, along with the pulse per second from the GPS, and also the serial data stream from the GPS, so that are all made available to the other side of the bus. This is the Allen deviation stability performance of the 10 megahertz output from 3 different Ublox receivers. The blue is the cheapest unit, which is less than $20. The violet is the last generation timing receiver that's probably $60 to $70 today. And the green is the current generation receiver, which has a lot of new features. And it's about $150. You can see that the more you pay, the better performance you get. So things are working as we might expect. We're going to make the clock module available with any of these 3 options installed. So it'll sort of be a bronze, silver, and gold, depending on how much you want to spend for the module. We fed the 10 megahertz output from the best quality of those receivers, the current generation timing receiver, into the Silicon Labs chip evaluation boards. And actually, I have two of those boards. One is for the 5335 series chips. The other is for the last generation 5328. The reason for that is that the evaluation board that's available for the older generation chip has a temperature compensated crystal oscillator, but the evaluation board for the current generation chip is just a bare crystal oscillator. We want to use a TCXO in our design. So the performance of the 5328 evaluation board with the TCXO is significantly better than the more modern board, but with just the bare crystal. The top 2 lines are the bare crystal, the blue and the green at 2 different loop bandwidths. The bottom 2 lines, the red and the violet, are with the TCXO on the older chip. And you can see the significantly better performance that we get with the TCXO. Now, the trade-offs of this design are these. On the Pro side, it's much simpler. There's no FPGA programming required, and the cost of the non-GPS components is much less. So that makes it less painful to use a better quality GPS module. And it gives us huge frequency agility with 10 outputs and any kind of frequency we want, basically from 100 kilohertz to a gigahertz. The con side is that the crystal oscillator that's used by the chip is in the 40 to 50 megahertz range, and it's quite difficult to find a wide range of choices of TCXOs or oven-controlled oscillators at that frequency, and they're significantly more expensive. So we don't have a lot of choice in the oscillators we can use to improve performance. And also, the Jitter Attenuator chip, PLL, has a loop bandwidth that goes out to about 1/10 of a hertz or somewhat less than that. And that's fine for moderate performance, but if we had a very high quality oven oscillator, we wouldn't be able to get a long enough loop time constant to get the maximum performance. So this design is not really capable of laboratory performance, but the performance that we're seeing is more than enough for the HF RF applications that we're targeting right now. There's also an issue with the fact that this design relies on the pulse per second signal that's coming directly from the GPS module for the timing side of the system. If the GPS signal is lost, the pulse per second goes haywire almost instantly. So it doesn't really have a holdover capability. And synchronizing to the pulse per second is more complicated. We can work around this in the FPGA of the data engine. So it's not a serious problem, but it is something that we need to take into account, and it does complicate things a little bit. We think, though, that that trade-off is worthwhile for all the other benefits that we get. So the status as of right now is that I'm still trying to finish the proof of concept. I really want to get a TCXO plugged into the 5340X evaluation board. But even if we're not able to do that, the separate testing we've done gives me a very high degree of confidence that this is going to work the way we expect it will. The schematic design is basically finished at my end, and I've turned it over to Scotty, who's pouring it into his CAD system. And from that, we'll generate the final schematic and start doing the board layout, which we hope will begin fairly shortly. My next project, now that this is finished, is to work on the carrier board for the TimeNuts crowd. So I'll be starting that design shortly. And that's about it. Thanks.
Hey everyone, my name is Michael Easton, or KK6OOZ, and I'm a lab tech for Open Research Institute. ORI is a nonprofit 501c3 research and development organization which provides all of its work to the general public under the principles of open source and open access to research. We do technical and regulatory work as well, as this past year we made some major strides forward for the amateur radio satellite service with a successful commodity jurisdiction request of the U.S. State Department. We received a final determination letter stating that open source satellite work is free of the International Traffic in Arms Regulations, or ITAR. These regulations control defense products, and the open source approach has been found as the best strategy for designing amateur satellites in the United States. The second part of that particular regulatory effort is going on right now. ORI is asking the U.S. Commerce Department to make a similar ruling about open source satellite work in the Export Administration Regulations. Indications are very positive that the news will be good for amateur radio. After all, we'll ask for something called an advisory opinion. This will tie the two results together and make them super clear. Another big area of regulatory work is debris mitigation. These rules are intended to reduce space junk, prevent explosions, and deorbit spacecraft as soon as possible after a mission is complete. More innovation and wider access to space are the expected results for the many commercial companies participating in what the FCC calls the new space race. The regulatory requirement for spacecraft to do more to avoid collisions means that attitude control and propulsion are necessary things to deal with for full access to space. Regulatory work is very important. It's part of ORI's commitment to the amateur radio service, but the motivation for all this legal work is so that we can have the most fun advancing the radio arts to the very edge of what's possible in innovative ways. We live in a time where we are capable of literally maximizing the number of digital bits we transmit over the air. These advanced communications engineering techniques allowing successful links at very low signal-to-noise ratios are not out of reach of interested amateurs. All too often, the most advanced wireless technology is secret, proprietary, or considered too complex for the mere hobbyist to master. But this isn't true. You don't have to be an expert to build or use these radios. You just have to be willing to become more of an expert along the way. And the focus of all this advanced digital communications work, it's not to write yet another paper or squeeze out another tenth of a dB in the lab. The focus is you, the operator. Let's talk about you. One of the most common complaints about digital modes is the voice quality. You don't want to listen to hours of scratchy, tiny compressed voice codecs that were designed for maximum subscriber revenue in 1997. Amateur digital communications should sound fantastic. There is no excuse for anything less. You should be able to instantly recognize the voice on the other side of the contact. Therefore, our user requirement is exceptional voice quality while still being efficient and smart about bandwidth. The solution? The voice encoder isn't built in. High-quality open-source voice encoding is layered on top of a solid digital signal. Do you want your contacts to sound like they were standing right there? You can choose that. You want to sound like a proprietary codec? You can choose that too, if you really want to. Let's talk more about you, though. Do you want a reliable amateur digital communication system that doesn't depend on an internet connection? A system that's fun and easy to use? A system that doesn't have 3 cryptic functions per button and won't need 9 steps to change a basic setting. We do too. Therefore, our user requirement is accessibility and ease of use. An accessible and easy-to-use system breaks down many barriers to learning. We don't believe people are motivated to learn more about digital communications when the radios are restrictive, sound harsh, are inflexible, or are just hard to use. An accessible system helps everyone enjoy the radio, not just people with low vision or who have trouble with fine motor skills. Software-defined radios can learn and adapt to operators in ways that we are just beginning to understand, appreciate, and implement. Imagine a radio that learns you prefer the backlight low, but the front large and the contrast high when you are monitoring a meetup conference or net. However, it learns you need a detail screen, brighter light, and lower contrast when searching for a roving station. The radio learns you would like a report or possibly a recording of who was on the satellite for the Thursday night net, even though you have to work late this quarter and will end up missing it. User interfaces for microwave radios like Phase 4 ground are significantly different from traditional microwave appliances. Legacy radios were fixed in form and function. Software-defined radios, however, allow for the radio to fit you. Machine learning techniques give a radio a little bit of soul. The Phase 4 microwave system automatically adapts to the structure of the transmissions to the needs of the link. This is called adaptive coding and modulation. The radio chooses the best possible combinations of modulations and forward error correction codes from a collection that covers all the expected signal conditions. When learning about any microwave technique or building up a system, one of the most useful things we have are beacons. The payload or central node of the Phase 4 system uses an open protocol called DVB-S2. This protocol is always transmitting digital frames of data, and when no one is talking, the frames are essentially empty train cars being sent one after another. They're called dummy frames in the specification. However, as amateurs, we love to fill up the quiet. We've put our dummy frames to use. When there is no user data, the dummy frames will cycle through all the modulations and codings so that new users and experimenters can test their receivers against all possibilities available in the protocol. It's like having a beacon built into the system. Whether the payload is on a satellite or a mountaintop, being able to make performance measurements like this is very valuable. Our transmitter designers have actually scheduled a demonstration in March of 2021. Here's a block diagram of what's required to make that demonstration work. A link to the repository is in the slides and in the transcript below. The transmitter demonstration uses a field programmable gate array, or FPGA. All the code is publicly available for others to use, learn from, modify, and even improve. We take data and organize it into frames. We provide extra data to help receivers find the start of each frame so that your receiver doesn't have to work so hard to bring it in. We use direct memory access to connect the processor to the programmable logic. We use something called an Advanced Extensionable Interface, or AXI, to connect different parts of the FPGA. The radio chip is from Analog Devices. We use the AD9361. We connect the radio chip with a high-speed interface. The languages for the FPGA design are Verilog and VHDL. These are computer languages that describe digital hardware circuits with software commands. When you compile this code and move it into an FPGA, the FPGA is physically reconfigured. Need to make changes? Load a different combination. FPGAs are an excellent fit for another really neat advanced digital concept, polyphase filter banks. We use polyphase filtering techniques on an uplink receiver, which is separated into frequency channels. When you are acquired by the system, you are assigned one of the uplink channels. Here's Michelle Thompson, W5NYV, to explain more about polyphase techniques.
Hello, my name is Michelle Thompson. I'm a co-founder of ORI and currently serve as CEO. So what is polyphase? It's all about using decimation and interpolation. These two techniques change the rate of the sample stream to accomplish some very clever work. That's why we call this type of work multi-rate processing. Decimation throws away samples. We might get rid of every other sample, every 5th sample, or every 100th sample. It depends on what we're out to do. Decimation reduces the sample rate. Interpolation inserts samples in between existing data. Those inserted samples often have a value of 0. We can upsample a sequence by a factor m by inserting m-1 zeros between each real sample. This increases the sample rate because we have more entries per unit time than we did before. We can also insert samples that are the average of the samples to either side. Here we have a signal that has been sampled. You can see the waveform in the upper middle of the whiteboard. We are going to make 3 polyphase out of this. We're marking them with a circle, a triangle, and a square. The sampling rate of these polyphase channels is 1/3 of the original sample rate. What does this do for us? In this example, we want 3 channels, and we need them to be sampling rate divided by 3 wide in frequency. We end up with 3 polyphases that we're going to name 0, 1, and 2. Now, we're in the realm of digital sampling, so things aren't quite the same as analog. There is a way to think about this that isn't too hard, and the way to think about it is here in this image. This is a rod and reel, like you use when you go fishing. You are reeling in the samples on the timeline, and when you wind up that timeline on your reel, the angular measurement, the thing you are winding with your hand on the reel, that angle around the full loop is something we call phase. A lot of us that volunteer for ORI are burners. This whiteboard was at math camp in 2019. We had a residency there where we were able to talk about these concepts to participants that wandered in and out of the camp. There is nothing quite like trying to explain polyphase filter banks to someone in a laser-encrusted moose costume at 4 a.m. to sharpen the pedagogy. Now, if Moose Man can understand it, then so can the rest of us in the cold light of day wearing ordinary clothing, which most days right now is fancy PJs. Touché, Burning Man. So here we are trying to explain it the ordinary university way, with rotating vectors coming at you out of the whiteboard. This was a disaster, and a mathematician from Austria made fun of us. It wasn't hard, we were making a mess of trying to explain it. But eventually we had our eureka moment. We called it rod and reel, but this must be something that has been presented before. We aren't claiming invention, but we do enthusiastically endorse this way of explaining digital sampling. If the fishing line is a timeline, and the digital samples are spaced out at equal intervals, then you can treat this like you are reeling in time and it's coiling up in loops on the reel. The diameter of the reel in the diagram reveals some very important concepts. What fraction of the rotation of the reel, the circle, do you traverse per sample? This is digital frequency. This is expressed in radians per sample. How far around the circle do you need to go to hit another sample? Notice that the diameter of the reel, the circle you're winding the sample train around, varies with respect to frequency. If you want the same number of samples per full rotation, this is an expected result. Large frequency means small diameter circle. Low frequency signals need a large diameter circle. Circumference is pi times diameter. The diameter is circumference divided by pi. The circumference of the circle is the time it takes for the full signal period. This is T of S. The diameter of the loop is T of S divided by pi. We have 4 samples per period here. When we reel in our samples and the diameter of the reel is T of S divided by pi, then the samples line up on the reel. This is super useful. Why? At the Nyquist rate, which is the limit of how often you have to sample a signal in order to be able to reconstruct it, you must have at least 2 points on the circle. That's the limit. You can't have a diameter of a circle with just 1 point in space. You need at least 2 points, and that is, visually, why the Nyquist limit works. Okay, so we have what's called critical sampling. This is the case when we have 2 samples on the circle of coiled up time. If we sample more often, we call this oversampled. It's the second one from the top on this slide. Undersampled, like we said before, is when you only have 1 sample on the circle. This provides not enough information to know what the waveform looks like. Tangles. Notice our polyphase colors are oversampled. We're going to use that fact to divide up the sample stream and get distinct channels out of this. Here's what this looks like in the frequency domain. Enjoy some ambient sound and check things out. Much of the center frequencies in these examples gets a phase shift. A shift in time is a shift in phase. We only calculate what we need, so depending on what channel we want to look at, we can throw away all the rest. Breaking down complex concepts into understandable and useful circuit designs and giving them away for free may sound crazy, but this has been the spirit of amateur radio experimentalism since the very beginning.
Hi, I'm Anshuman. I contribute to a few of the embedded projects for ORI, and also I am researching on debris mitigation for our next space mission at ORI. In the past, ARSS community has done various has provided various non-commercial effort, has been involved in various non-commercial efforts, which have led to this CubeSat and small-sat revolution. But in this new era, there are few more challenges due to commercialization of the space. And one of the challenge relates to debris mitigation. And this will be my focus point for my talk at Ham Expo. ARSS community should not be limited to only LEO orbits. In no way I'm saying that LEO orbits are less important or less effective. They have high educational values and are good for experimentation. But if we see the dream of providing communication across the globe 24/7, then this GEO orbit provides us with the perfect opportunity, as it provides us with a space stationary point to which our Earth stations can point and have the regular communication. To achieve this goal, to reach that height, we need to abide by the rules framed by FCC. In my talk at Ham Expo, I will be giving a GMAT demo for planning your mission, which will show a graphical representation of planning your mission to meet the requirements of FCC regarding debris mitigation. Also, I will present a mathematical paper which will decipher how we can calculate delta V, propellant budget. All these will help you to plan your mission in a most efficient and effective way, along with meeting the guidelines framed by FCC. So please join me at Ham Expo 13th of March for my talk. Thank you.
Okay, that concludes our ORI TAPR hour. I see we have some questions that look like they are pretty much answered on the chat room, the chat window. Any other questions? Okay, let's see.
Scotty, there's a comment in the group chat about from John saying the last graph showing the crystal oscillator and TCXO stability seems like the legend showed a different reference that indicated. I'm not sure when you posted that for being the last graph, but the reference that's shown in the Allen deviation plots is the external reference that's being used to compare against. That was a cesium atomic clock. So that's not part of the clock module. It was the external thing that we were measuring the clock module performance again. So I hope I understood your question and that answered it.
Okay, I see another question. When will the Tangerine SDR be available? We're looking to have prototypes built and running full radio by Hamvention. So the middle of May. And I'm not sure how long after that we'll have actual hardware for sale. But I guess it'll depend a lot on how good a job we did on the hardware and whether we find any mistakes or not. Okay, the clock module question about the external oscillator, that was answered. It will take an extra clock module will take an external oscillator. You, John, do you want to elaborate on that at all?
Sure. We're trying to put as many spigots for I/O as we possibly can on the board. And actually the chip that we're using has 4 inputs. You can only select one at a time, but we're going to wire those up so that one of them is available for an external oscillator to, if you want to bypass the GPS signal.
Okay, do you see any other questions? Anyone?
And I'm just looking, Bob McGuire just posted, there's a question about one of my charts and the legend being wrong, which is entirely possible, but I don't know which chart we're looking at right now. So I'm not sure if I can comment on it unless somebody can tell me which of the charts it was.
Yeah, John, I don't have your PowerPoint, so all I have is
Yeah.
the movies. So
But and right now, Scotty, I'm actually opening the presentation up. But if somebody answers with which chart they're referring to, I would appreciate that, because then I can point to it. I certainly I don't doubt that I might have a label or a legend incorrect.
the
Yeah, we
comment
can-
says go to the last chart.
Okay.
In the mean,
Bear with me.
advice for learning FPGA software. FPGA learning is notoriously difficult because it's where you blink an LED, do some sort of very simple signal in FPGA software, which itself very difficult in many cases to install. And the 2 main spheres that we deal with for FPGA are the open source tool chains, which have come along dramatically and well over the past breaker, ice storm, and that sphere, which can be tricky to install. And then there's also Link's Vivado, the big professional suite. And structural educational problem with FPGA development, in that the very easy stuff is easy to do. You get a pre-factored template that lets you do something very simple, and then there's this enormous gap in between, and then there's all these people doing professional PhD dissertation work. And part of the job as us as 501c little in that middle part. So after you get the skills of blinking an LED or doing a simple clock, what comes next? So up here, and there are immediate middle layer, middle level things and doing, but the challenge is real. The question is very relevant. There's a lot that covers the very easy, and there's a lot that covers the very advanced. Stitch the 2 together. That's one and ORI are actively working on to figure out how to deliver to the community. So in terms of advice on learning FPGA software, dive in. There are some online on-demand learning from Xilinx. this is pretty good. And the community, the icebreaker community, is the place to go and ask for help with getting beyond.
Okay, you're breaking up a little bit here, Michelle, but I think we have a hard stop here at 10:54.
Can I just quickly jump in to answer Bob's and the others' question about the chart?
Okay.
If we have a second. The chart is correct. I'm not sure what you're seeing is wrong, but there are two curves for each of the two evaluation boards with two different loop bandwidths. And the 5328 board has TCXO. The 5342 has XO. They're all being driven from the same receiver with different bandwidths. And the reference, the HP 5071A, is the external reference that we were measuring against.
Okay, very good. Any further questions on Tangerine can be directed to tangerinesdr.com. And for Michelle, it's ORI, Open Research Institute.org. No?
No, it's openresearch.institute.
Institute, openresearch.institute. Okay, very much. Very well. Thank you, everyone. And this concludes our presentations.
Thanks, folks.
Hi there,
So-
Anthony here at Gigaparts. Wanted to tell you all
Oh,
about
boy.
the amazing radios that we offer here at Gigaparts, offering power supplies and other accessories. Gigaparts also carries refurbished computers from names that you know and trust, such as Dell, Lenovo, and HP. They make excellent ham shack PCs. We carry 3D printers, filament. We also have amazing zero PCs. PCs with zero bloatware, zero compromises, and zero worries. If you're curious what else we stock, be sure to visit us at gigaparts.com.